Hi everyone, my name is Gaz. I'm a technical engineer here at Maxon UK and Ireland. Welcome to part 2 of Maxon Datasheets Explained. So why are datasheets important? Well, the fundamentals of every application is the requirement of speed and torque. And in Maxon's datasheets, you'll find all the necessary data for your motor selection process. In this video, we'll focus on two particular motors, the RE35 brushed motor and also the EC45 brushless motor. Let's have a look at the RE35 brushed motor datasheet. We'll be focusing on the first 5 windings. If you have a look at the first 5 windings, you can see nominal voltage is the first rating that you see. This is mainly what each winding is tested at, and the data underneath each column represents this. Voltage is important when looking at speed requirements for your application. On the Maxon datasheet, you can find the no-load data for each of the windings. These tend to be fairly similar throughout the range. If you look further down, you can see the speed constant. This represents what speed is achievable per volt. So in order to get a theoretical value for the no-load speed, we can do, say if we take the first 15 volt for the example, we can do 15 volts times 491 RPM per volt, which will give us 7,365. This is our theoretical value. But if you look on the datasheet, the actual no-load value given there is 7,200. This is what is derived from the testing at our factory. If we now have a look at the 42 volt version, that has a speed constant of 182 RPM per volt. So if we do 42 volts times 182 RPM per volt, we get 7,644. And again, for that, the data on the datasheet is 7,580. So these are all figures that have been tested, so we can guarantee those. But in a real world scenario, say we look at a 24 volt power supply. Let's take the same examples, the 15 volt and the 42 volt. So if we apply 24 volts to our first winding, so we do 24 times 491, which will give us 11,784. And for the 42 volt version, let's do 24 times 182, which will give us 4,368. So here you can see there's a huge difference between these two values at 24 volts. The lower end winding is double the speed, whereas the higher end winding is half the speed. So you can see from here, when you come to select the correct motor for your application, you need to choose the correct winding. And this primarily focuses on the speed constant. So there you go. This is a point that you must always look at when selecting your winding. Now let's move on to current. This is directly proportional to torque. If you look on the Maxon datasheet, you can see nominal current rating. This is the current that the motor can be run at continuously, safely. And this is directly proportional to the nominal torque. If you come further down, you can see this also has a constant value, which is the torque constant. This shows you per amp what torque is achievable. So we'll take the same examples again, the 15 volt and the 42 volt. So if we come down and look at the torque constant for the 15 volt, this is 19.4 millinewton meters per amp. And the 42 volt is 52.5 millinewton meters per amp. And you can see there's quite a difference between these two. But if we go back and look at the nominal current rating, the 15 volt is 4 amps and the 42 volt is 2.07 amps. So if we were to do a calculation to find out what the achievable torque for the two windings are, we'll go and do 4 amps times 19.4, which gives us 77.6. And then if we do the same for the 42 volt, which would be 2.07 times 52.5, that will give us 108.68. So you can see from here, they're roughly the same. And then if you look along the datasheet, you can see the torque ratings are more or less the same for all the windings. And then you also notice there's an actual nominal torque rating, which is the tested value from the factory. So for the 15 volt, it's 74.2, and for the 42 volt, it's 105. If we compare that to our calculated values, they do differ slightly. This is purely because our calculated values are theoretical. So now if we move on to a real life scenario, say an application where your power supply can only produce 1 amp of current, and if we apply that to the 15 volt version, we can see that we can achieve 19.4 millinewton meters of torque. And then if we apply that same 1 amp to the 42 volt version, we can see we can achieve 52.5 millinewton meters. As you can see, when we apply the same current to both windings, the achievable torque differs. It almost doubles for the higher winding. So you can see here why these data points available in our data sheets need to be considered when it comes to your application, as it can really change what torque's achievable. Although you're given the same current, the torque differs quite hugely, almost doubles in the higher windings. There are other useful data points to consider on the maxon data sheets. Let's look at no load current. The no load current is what the motor draws when it's run throughout its speed range without any torque applied. So at the higher end of the speed, what you'll notice is the no load current will be closer to what's in the datasheet. As you reduce the speed, the no load current should reduce. As long as it's below the stated no load current, it's safe to say your motor is running as expected. So this is a good test to do if you're wondering whether your motor was faulty or you feel it's not running correctly. This kind of ensures it is functioning as expected. Another data point to look at is the speed torque gradient. This is derived from the speed constant and torque constant. If you were to plot both of those on a graph, you either get a steep line or one that's more in level with the x-axis. The one that's more in level with the x-axis indicates that it's a stronger motor. So throughout all the windings, you'll notice the torque will be more or less the same. Whereas with one that's steep, you'll notice that the torque will differ throughout that range. So as you go up in the winding range, it will differ. So this is something to consider if you were going to take multiple motors throughout a single range, say the RE35, and you wanted all of them to have the same torque. So this is quite useful in those kind of scenarios. The next point we'll look at is the thermal data for the RE35. This data is available for all our motors. This gives an indication of how much you can push a motor further than what its nominal ratings are. So in our case, you can see it's 30.1 seconds. So this particular RE35, you can push beyond its nominal torque for about 30.1 seconds. But when doing this, you should realize that there's going to be heat generated. The more heat, the more likely that the motor is going to get damaged. So this is something to be careful of. There will be a follow-up video which will explain motor thermal data in more detail. So if you want to learn more about the thermals behind motors, then subscribe and then watch out for our next video. Thank you for listening.